All right, so we're going to go example 8. And what example 8 is, it's kind of algebraically discussing multiple ways to achieve the exact same graph, right? There's more than one way to skin a cat, as they say. There's more than one way to eat a Reese's peanut butter cup. And there's more than one way to sketch a graph, okay? So what we're going to do is we're going to start with a parent function, and we're going to be given a transformation, okay? We're going to describe what that transformation does. And then we're going to algebraically manipulate the equation to see if we can get it equivalently. All right. So before we start, again, remember that the standard transformation form is A times F of B times X minus C plus D. Okay. Where, of course, F of X is your starting function. And y'all had a lot of experience with this in Algebra 2. So remember, we got the inside piece and we got the outside piece. Right? The inside pieces affect the graph horizontally because they affect the X values. And then the outside pieces, the A and D, are affecting the graph after you find the Y values. So those are affecting the graph vertically. So if we start with the graph of X squared, and we won't necessarily sketch this for all of them, but of course, in the beginning, it's probably worth doing. So here's what the graph of X squared looks like. You know that Y equals X squared. If I sketch this new function G of X, that is 4X quantity squared, first of all, what does this transformation do to the graph of X squared? Is that 4 on the inside? Is it an A, B, C, or D value? It's a B value, right? What does it mean to be on the inside of a squared function? It means to be in the parentheses before you square it, right? If you were to actually evaluate this, you would choose an X value, and the first thing you do would be multiply by 4, right? So you're affecting the inputs, not the outputs. So what would that 4 do? It would be a horizontal dilation. Would it be a compression or a stretch? Compression. Remember, we said yesterday that anything on the inside is the opposite of what it appears. So it's not 4 times wider, it's actually 4 times narrower. So it's a horizontal compression by a factor of 4. Okay, so let's see what that's going to do to the graph. If I horizontally compress it by a factor of 4, every value is coming in 4 times what it used to be. 0 stays put, okay? That's going to effectively make the graph steeper. You see that? Think about horizontally compressing it, taking the original green values and putting your arms on either side and pushing it towards the Y-axis. That's going to make the graph steeper, yes? Okay. Now, there's another way to obtain the same graph. If you notice, we could equivalently, instead of pushing it horizontally towards the Y-axis, I could grab the Y values and stretch them upward vertically like that. See that? I can pull the Y values upwards from the green graph to still get the blue graph. So there is going to be some vertical stretch that will equivalently give me the same graph as the horizontal compression. But what would be the scale factor? Well, that's where the algebra comes in. Let's come over here and write G of X equals quantity 4X squared. Every function is going to be unique. I want to essentially try to rewrite this a different way. So 4X quantity squared. Can we simplify that? Well, I can't just get rid of it, but I can't really divide it. But I could say that 4X quantity squared is the same as 4X times 4X, yes? And then now I can multiply like factors. What's 4 times 4? 16. X times X is X squared. Yeah. So what I did is I took the 4, which started as a B value, and I've turned it into a 16 on the outside, which is now a what value? A, B, C, or D? It's an A value. Yeah, it's multiplied outside the square function now. So that's an A value. So that's going to be equivalently a vertical stretch by a factor of 16. Yeah, there you go. So if you start with X squared, you can get the graph of G of X 2 different ways. You can horizontally compress it by a factor of 4, or you can vertically stretch it by a factor of 16. They're both going to give you the exact same graph. Okay. Make sense?
That just means you can mathematically determine the step when you want to.
Yes, absolutely. The mathematics that we're manipulating the original equation is how we're getting the second transformation. We knew it was going to be a vertical stretch. We just didn't know the scale factor until we did the mathematics. Okay. All right. Let's do it again. We're starting now with the square root of x. Square root of x. So let me just sketch that. We'll do that in orange here. There's y equals the square root of x. Now, what I want to do is create this new equation. G of x, that's 4 times the square root of x. This 4 is inside or outside the square root function? It's outside. It's multiplied, so it's an a value. So that's going to be a what? Vertical stretch by a factor of 4, right? Vertical stretch by a factor of 4. So look what that's going to do. It's going to take all your y values and multiply them by 4. Well, 0 times 4 is 0. 1 times 4 is 4. 2 times 4 is 8. 3 times 4 is 12. If you connect those y values, it has the effect of making the graph steeper, doesn't it? Which is what we would expect. Now, let's graphically look to see if there's another way to do it. I can equivalently, much like the previous example, I can get the exact same graph by taking my x values on the orange graph and compressing them to make the green graph. You see that? So instead of grabbing it vertically and pulling, I can put my hands on either side of the y-axis and push. So I know that it's going to be equivalent to a horizontal compression by a factor of something. How are we going to find the something? Well, we're going to algebraically manipulate the equation. So let's come over here. Let's write g of x equals 4 times the square root of x. Now, because I know it's going to be a horizontal compression, I know that what letter does the horizontal dilating? A, B, C, or D? B, right? If it's horizontal, it's on the inside. Okay. If it's a dilation, it's multiplied. There's only one letter on the inside that's inside multiplying. It's B. So I got to somehow get the 4 inside the square root. But here's the deal. It has to be equivalent. I can't just say, oh, I could take the 4 inside, sir. Just watch. Look, I'm a very helpful person. I'll just take it inside. Well, that's great. But those aren't equal, right? Those aren't equal. So my question is, what factor on the inside of the square root function is equivalent to a 4 on the outside? It would absolutely be a 16, because what's the square root of 16? 4. Yeah, there you go. So now we know the scale factor. For this function, to get the graph of g of x from f of x, you either A, vertically stretch it by a factor of 4, or B, horizontally compress it by a factor of what? 16. Yeah. Yeah. And you can see that the horizontal compression is going to be a larger scale factor than the vertical stretch, because notice the little lines that I drew horizontally, they're longer, aren't they? Those are actually like vectors. So the longer the line, the greater the magnitude. Okay. You see what we're doing? Now we're doing it graphically so we understand what we're doing, but we're not always going to have the luxury to be able to do it graphically. We want to see if we can continue to do it algebraically. Okay. So let's go ahead and do that. No more graphing. I'm starting with the graph of 3 to the x, and I want to end up with the graph of 3 to the x minus 1. So the first thing I'm going to do, very good. The first thing I'm going to do is just look at that. That's your c value. So I'm going to take the graph and move it right 1. That's the first way that we're going to do it. Now, what I need to do is see if there's an equivalent way to algebraically get the same thing. So what we'll do here is we'll start with g of x, just like we did before, x minus 1. And I'm going to try and get that minus 1. I'm going to try and equivalently maneuver that equation so that it's equivalent to something else, but not in the exponent. So for an exponential function, we can use the property that says when the bases are the same, we add the exponents. But we're going to use it in reverse. See that? We're used to using that rule this direction. 3 to the something times 3 to the something is 3 to the add up the exponents. But it works the other way. We can decompose the exponents, yes? Okay. Now I can simplify that. That's 3 to the x times, what's another name, or 3 to the negative first? 1/3. Good. And now because that 1/3 is multiplied, I'll bring it to the front. 1/3 times 3 to the x. And now it's an a value. So for this function, apparently, moving the graph right 1 unit is equivalent to a what? If it's an a value, it's got to be a vertical compression by a factor of what? 3. Good. If your scale factor is ever less than 1, you just flip it. Okay. So there you go. For an exponential function, you can move it right a unit or vertically compress it by a factor of 3. It's 1/3 as tall. There you go. You got the idea? All right. Go ahead and try this one on your own. Oh, wait. That might be a little harder.
He is not that bad. He is not that good at all.
Oh, yeah, that's getting worse. Well, maybe if we do D, you can do E. All right, so this kind of ties into what we learned the other day about the difference between the bases when they're both growth. Which graph grows faster for large values of x? 3 to the x or 9 to the x? 9 to the x, but they do intersect at what ordered pair? 0, 1. Good. So what I want to do is start with the graph of 3 to the x and somehow make it steeper so it becomes the graph of 9 to the x. So it's not real obvious what the first transformation is anymore, because g to the x is not in terms of 3 to the x, right? So my first goal here to get the first transformation is try to write 9 to the x as 3 to the x to the something. So that's what we're going to do. We got 9 to the x. Well, I know that I can rewrite 9 as a power of 3, right? What is it? 3 squared. Yeah, there you go, 3 squared. And now I know that when I raise a power to a power, I do what with the exponents? Multiply. Good. So I get 3 to the 2x. That's another name for g to the x, but now it's in terms of f of x, right? So now I can get my first transformation. Well, is this too an a or a b value? It's right in front of the x, right? X is the horizontal axis, isn't it? So it's got to be a horizontal dilation. It's got to be. So this is a b value. B is always the horizontal dilation factor. So it's a horizontal what? Stretch or compression? Yeah, we don't do that. We always, it's a vector. Compression means smaller, stretch means bigger. We're horizontally compressing it by a factor of 2, right? It's not twice as wide as you would think. It's on the inside. Remember, to be on the inside means to be in the exponent. So it's the opposite. It's twice as narrow. So to do that, we compress it by a factor of 2. Okay. Now, is there another way to achieve the same thing? Yes? Okay. Well, let's see if I can rewrite that still as a different power of 3. 3 to the 2 times x.
3 squared times 3x, or 3 to the power of x.
I've got to either turn the 2 into an a or a c or a d value. I don't really know how I can do that, aside from calling it 9 to the x again. I don't really know a way I can do that. Yeah, I think that's about the only one we can do. Okay, let's see why graphically, since we are talking about exponential functions. If I were to sketch 3 to the x, 3 to the x would look like this. Y equals 3 to the x. Okay, if I graph 9 to the x, let's just go ahead and graph 9 to the x on there. I know from that diagram yesterday that it's going to look like this. Okay, that would be y equals 9 to the x. Good. Yeah, they cross at 0, 1. 9 to the x goes to infinity faster, it goes to 0 faster. What I just said is I can get from the purple graph to the green graph by taking the purple graph and compressing it horizontally, right? Towards the y-axis. And you can see that that makes sense now, doesn't it? That would leave the y-intercept alone, wouldn't it? Because your hands are on either side of the y-axis, pressing it towards the y-axis. It doesn't change the point on the y-axis. So that makes sense. Well, that would be kind of the only way we could do it, right? I think because, well, look what happens. If I do a vertical stretch, what's going to happen to my Y-intercept if I take the Y-intercept on the purple graph and I vertically stretch it? That's going to change the Y-intercept, won't it? And I can't do that. That's not allowed. They have to share that point. So I can't vertically stretch it because that'll change the Y value from 1 to something that's bigger than 1. Okay. So if I don't have a vertical stretch at my disposal, all I have are shifts at my disposal. Well, a vertical shift isn't going to work, is it? Because that's going to change the horizontal asymptote. So my only other opportunity would be a horizontal shift. Well, look what happens when you do that. It shifts off the, yeah, the Y-intercept changes, right? And that's why up here on this one, we saw that a move to the right or left translated into a vertical dilation because it does change the Y-intercept. So now I can pretty much conclude graphically that there's not a vertical dilation, a horizontal shift, or a vertical shift that's going to accomplish the goal. The only way to get from 3 to the x to 9 to the x is by a horizontal compression by a factor of 2. Okay, so not all of them have 2 different ones. All right, let's just, for the sake of time, I think we just have to boogie, right? So let's just do this one together as well. Now I want to get from 3 to the x to 9 to the x plus 1. Ooh, well, first steps first. Just like before, I want to write 9 to the x plus 1 in terms of 3. So we'll do the same thing. I'm just going to replace the 9 with a 3 squared. Okay, and then I'm going to simplify that. When we raise the power to a power, we multiply. But here's the deal. I'm not going to distribute the 2. I'm just going to multiply it 2 times the quantity x plus 1. The reason we don't want to distribute the 2 is because this is still in standard transformation form. It looks good. So now I have a way to talk about getting from 3 to the x to 9 to the x plus 1. Okay, what does the 2 do to the graph of 3 to the x? Horizontally compress it by a factor of 2. But then I have another one to do after that. Then, right? Then left 1. Yeah. Good. So I have to do 2 things. I have to do 2 different things. Now, is there another way to do it? Well, we saw in the other one, no, but I can actually borrow a page from what I did right here on part C. If I have 2 terms in the exponent, I can split them up into their own factor. So now what I'm going to do algebraically is distribute this 2. Since I already got my first one locked in, let's go ahead and distribute the 2. That gives me 2x plus 2. Now that's not standard transformation form anymore, but what does it now allow me to do? 3 times what? 3 to the second. Very good. Very good. 3 to the 2x times 3 to the 2th. And now 3 to the 2th, I know is another name for what? 9. And I can pull that to the front because now it's multiplied on the ground floor. And now I've got another transformation that's in terms of 3. So if I do these from left to right, what would the 9 be now? What letter? It's an A value. Good. So it's a vertical stretch by a factor of 9. Then a horizontal compression by a factor of 2. Okay, there you go. Isn't algebra fun? Yeah. Hello, Cole. Oh, King Cole was a merry old soul, and a merry old soul was he. All right, where can you go to practice problems of that nature? The worksheet, right. And you can do that worksheet pretty much anywhere. So you can go to like Target and do the worksheet. Well, there's a Starbucks at the one at Creekside. Yeah. And if you walk in and go around the corner, there's a whole line of seats right on the window there. You can kind of. They won't be mad about you over there because, well. I'm pretty intimidating, right?
No, you can just order a coffee and then.
Oh, yeah, there you go. Oh, you don't mean me. You mean like one.
Yeah.
Right.
They'll just let you.
Be a patron of the restaurant and then you can loiter, right? Yeah. But maybe after a couple of weeks, they'll be like, dude, you need to either order another coffee or go home and shower before.
Okay, maybe not there for a couple weeks, maybe like an hour or two. Not a couple weeks.
Right.
Because you're probably getting a tank from that.
Yeah, you can say, hey, Starbucks, do you ever think about like installing a shower
No.
in this?
Shower should only be used for.
Well, there's restrooms right around the corner, right? So I guess you can go in there and take a shower in the sink. Yeah, I guess so. I don't know. I've never even literally been to a Starbucks before, but I've heard about them. All right, let's move on to example 9. We're shifting gears here. So the Starbucks story was just a good transition. Find the exponential function of the form f of x equals b to the x whose graph is given below. So this is the scaled down simplest version of an exponential function, right? Because normally we look at f of x equals a times b to the x, but in this case, we don't see the a, so we know it's implied to be 1. So what's the y-intercept of these two graphs down below, supposedly? It's got to be 1, right? Okay, so this has got to be the point 0, 1. And this has got to be the point, hello, Merry Christmas. And this got to be the point 0, 1 also as well. So, haben Sie Fragen? ¿Tienes preguntas? Do you have any questions? Or you're just here to hang out?
Oh, I was here to take the quiz.
Oh, the quiz. Oh, okay.
But I can also sit in advisory.
That would be easier actually. Is that okay? Yeah, okay. All right. Yeah. All right, so 0, 1, 0, 1, and let's see, it's growth, right? This one's growth, so we know it's got to be what? Increasing or decreasing? Increasing, so we know the base has to be what in relation to 1? Bigger or smaller? Bigger, okay. Now, you could think of this as like a formula. I'm going to replace f of x with y. Y equals b to the x. There's 3 unknowns here, right? 3 unknowns, a y, a b, and an x. If you're trying to solve an equation with 3 unknowns, you need to know 2 pieces of information because you can only have at least 1 unknown with a single equation. You've learned that in your science classes, right? Solving. So if I'm trying to come up with a b, that means I need to know an x and a y that satisfy the equation. Well, I have 2 points labeled on the graph. So those are both x and y coordinates that satisfy the equation, right? Not unlike a Snickers bar would do, right? Let's go ahead and try and plug in this point here. We're going to say at the point 0, 1, colon. This is how you communicate that you're plugging in this point. So I'm going to plug a 1 in for y, and I'm going to plug in a 0 for x, and I'm going to try to solve for b. Here we go. What is b to the 0th power? Nope. What's anything to the 0 power except 0? 1. Yeah. Hey, and I end up with 1 equals 1. True that. That doesn't really help me, does it? Doesn't help me at all. The variable went away. So that must not be the point that I need to use. Let's try the other point. At the point 225, okay, I plug that in there, and I get 25 equals b to the 2th power. Oh, now I can solve for b. It's a quadratic equation. I have to take the square root of both sides, don't I? And remember, when you take the square root, you always at least consider plus or minus. You always at least consider plus or minus. So that gives me either b equals -5 or b equals +5. Do both of those values work, though, in the context of this problem? No, why not? Can we have a negative base on an exponential? No. The base has to be strictly between 0 and 1 to be decay, or strictly greater than 1 to be growth. You can't have a negative base. So we considered it, and then we purposely tossed it aside. So b equals 5, okay? So the equation of this graph must be 5 to the x. What you do is you plug that back in up here for b. And you could probably figure that out just by looking at it, right? 5 to the 0 is 1. 5 to the 2th, 5 squared is 25. But that's your systematic algebraic approach. All right. Now that you know how to do it, you go ahead and do b on your own. On your mark and set, go. I'm going to do it quietly up here, and we'll compare answers. No, I'm not going to freeze the screen. I just want y'all to have a high emotional quotient. Don't look up here until you're done. Don't look up here until you're done. I will freeze the screen, Brady. I don't trust y'all to have a high emotional quotient. It's too tempting. It's too tempting, right? I'm going to look in my stocking to see what St. Nick brought me before St. Nick Day. Oh, it's still empty. Got to wait for the coal. The coal, get coal. Yeah. That'd be funny if you said, hey, you're getting coal in your stocking for Christmas, and you go check, and instead of like a piece of like black anthracite in there, it's like coal. He's like in your stocking saying, hey, happy St. Nick Day, right? Got coal in our stockings. Yeah, that should be a new thing.
Found it, but it's very janky.
Janky. No, that's not. Oh, hey, when we take the cube root of a number, or the fifth root of a number, or the odd root of a number, do we need to consider plus or minus? No, no. That's only for evens, because remember, evens can still pair up and be two negatives can make a positive, but not for an odd root. So we don't consider plus or minus. So it is only the one that you get with the positive. So yeah, if you plugged in 0, 1, again, you're going to get a true statement, 1 equals 1. So we're going to use the other point. Plug it in, you get the cube root of an eighth, which is a half. So the answer is y equals 1/2 to the x, or we can write it as 2 to the negative x. Yes? Same thing? We saw that in that picture up above. 1/2 to the x and 2 to the negative x are the same, because it's just a reflection of 2 to the x across the y-axis. Or you can write 1/2 as 2 to the negative first, and then combine your exponents. All right, so that's kind of those are the easy ones. Those are the easy ones because the a value is 1. Are you ready for the fun ones? Yeah, I am too. All right, letter 10. Write an equation of the exponential functions in the form a times b to the x that pass through the following points. Well, again, if you want to, you can replace f of x with y. And now you have 4 unknowns. See that? A y, an a, b, and an x. If you have 4 unknowns, you're going to need to know 3 pieces of information to find the one unknown. Or, since I really want to find what the values of a and b are, you can have 2 pieces of information. Okay? You really need to have as many pieces of information as you do unknowns if you don't have all but one. So with needing to find a and b, that's 2 things I need to find. I need 2 pieces of information. So we're going to have 2 ordered pairs. So let's look at letter A. We got the point 0.04 and the point 422. Now, if you want, go ahead and write the form right above it, just so you can see it again. Are either of those 2 ordered pairs anything special? Yes. Which one? 0.04 is very special because that is the what? Y-intercept of the graph. So do we know what A is right off the bat? What is A in the equation? Isn't that your starting value? Isn't that your Y-intercept? Yeah. So right away, if you take inventory, you know that A has to be 4. Yay. Now, what if you didn't make that connection? Is there another way to do it? Yes. Let's plug it in at the point 0, 4. We're going to plug in a 4 for y and a 0 for x. You get 4 equals a times b to the 0th power. And what is b to the 0th power? 1. And what's a times 1? A. So there you go. You get a equals 4. It's just a little bit faster if you realize right away. So now you're like, oh, I've got a. So if I plug that back in up here, so now I have y equals 4 times b to the x. So I'm getting closer to getting the equation, but I still have one unknown value of b. So I need another piece of information. Oh, that's exactly what we're going to do. We only need 2 pieces of information. You can have more than 2. So now we're going to plug in that to get the second value. All right. So now we're going to say at the point 522.
Good morning, and pardon this interruption. This is for all students. Students, we are not allowing classes to go to the gyms today during the tournament. Students, we are not allowing classes and students to go to the gym today during the tournaments. Thank you.
Yeah, you're welcome. Okay, so I plug in the other ordered pair and I get this simple little algebra equation. Okay, we need to solve for b to the 5th, right? So what I need to first do is get b to the 5th by itself. It's currently multiplied by 4. How do I undo multiplying by 4? Divide by 4. So I'm going to switch sides as well. If I divide the right side by 4, it divides out, and I'm just left with b to the 5th. And on the other side, I get 22 divided by 4, right? Which that doesn't go in evenly, does it? But can I simplify it? Yeah, there's a common factor of, yeah, that's 11 over 2. And now, how do I undo raising something to the 5th power? Not the square root of 5. We call it the 5th root. We take the 5th root of both sides. The 5th root of b to the 5th is b, and we end up with the 5th root of 11 halves. Okay. Now, that is, to quote Lenny over here, that's a janky base, right? Yeah, but I could plug it in, right? I get y equals 4 times the 5th root of 11 halves to the x power. Ooh, that's a disgusting base.
Yeah, I don't think that'd be easy to calculate back out later. Also, what'd you rate? You're at 3 for the 5th.
Oh, why did I do that? There you go. Now it's even jankier, but correct. Yeah. So that would not be incorrect, but can we pretty that up a little bit? Yeah, possibly so. Right now, the 5th root of 11 halves is an irrational number. Let's see if we can make it a little prettier. Okay, and this gets back to the algebra we were doing earlier when we were writing equivalent transformations. I can write 11 halves as 11 halves, and now the 5th root, I can get rid of that and put it as a fractional exponent, right? To the 1/5 power. See that? And now I can multiply these two fellas together. So now I get 4 times my base 11 halves to the 1/5 x. And that's a lot prettier because now my base is 11 halves, which is a rational number instead of an irrational number. And now I can just say, oh, how am I going to get the graph from the parent function 11 halves to the x? I'm going to vertically stretch it by a factor of 4. Let's go ahead and write that. This would be a vertical stretch by a factor of 4. And what would the 1/5 be? It would be a horizontal what? Stretch, because it's opposite of what it appears. It's not a 5th as wide. It's 5 times wider. So it's a horizontal stretch by a factor of what? 5. Yeah, if it's not bigger than 1, you flip it. Okay, and that's a lot better. Okay, so there's the equation. If you had an equation, if you had a problem like this on your test, and you will, this would be the answer choice. Okay, I'm not going to leave it as a janky, irrational base. Okay, so don't be afraid of tidying up your work on the back end, right? All right, I think we got time for one more. You go ahead and do letter B on your own. Yep, that's good. Yep. All right, let's go over this real quickly, and then I've got some things for you to work on here. Okay, so you plug it in, you're like, hey, A equals 2, because you're given the ordered pair 0, 2, right? Nice. Or you can do what we did the last time. Plug it in, you'll get A equals 2. So that when you plug that in, you want to kind of continually be plugging things in as you find them so that you're chipping away at the equation. So once you plug the 2 in, now you still need to find B. So then we say at that point, you plug it in, you end up with the cube root of a fourth. Okay, a half of a half is 2. A fourth, sorry. A half of a half is a fourth. So we get this equation right here. Y equals 2 times the cube root of a fourth, all to the x power. But look at that. Yucky, yucky, gross, gross. That's an irrational base. So we write 1/4, or the cube root of a fourth, as 1/4 to the third power, right? And then we use that rule that says when you raise a power to a power, you multiply, and you end up with 2 times the fourth, which is a really nice rational number now, to the 1/3 x power. All right, and that would be the answer. Okay, so we're done now. We're not going to do anything more with these notes, so you could submit them, but I do want you to make these changes to the worksheet. It'll make the worksheet a lot easier. On number 9, question D, change this ordered pair from -2, 3 to 0, 3. Okay, in other words, just get rid of that -2 and turn it into a 0. And on the second one, part E, get rid of the point -1,4 and turn it to 0, 4. So basically what you're doing is like what we just did. You're making that first point that I give you 0, something, okay, instead of another number, something. Those get a little bit too difficult, and I won't put anything like that on the test. So these are on the worksheet. Yeah, worksheet number 9, questions D and E, change the first point's x value to a 0. All right. And then the other part that we're leaving off, which is this logistic function, your worksheet doesn't even have anything on logistic on it. We're going to talk about that in the next section. Okay. So we did finish the notes today with a little bit of modification. You should be able to do all of your worksheet now if you make these changes. So the worksheet is going to be due tomorrow. Okay. And we will have a quiz tomorrow as well. Worksheet 4.1. All right, any questions? All right.
So, a final question.
On your notes? Well, you can do the entire worksheet now. You just change number 9, D and E, to those 2 ordered pairs, and then you can do the entire worksheet. All right. All right, have a good one.